Guy, hello. Kiev is speaking. How are you?
I'm doing good. How are you doing?
I'm perfect. Actually, I read some of your biography, and I know that you have interesting facts in your biography. I wanted to discuss with you.
Absolutely, absolutely. I stand by everything in my biography. None of it are lies. Yeah.
Great. So, I know that you educated somebody in prison. What is the story about?
Yeah. So there's a prison. I'm here in Columbus, Ohio, and there's a prison about a 45-minute drive north of here, where there was a programming curriculum, and I went into the prison and I taught a group of about 20 men JavaScript and Java. And
Wow.
many of them got out since then. A couple of them are doing really well. One even landed a job at Google, which is
Wow.
really, really, yeah,
This is
it's very
amazing.
cool.
This is unbelievable.
Yeah,
Great.
it's nice to be part of the solution.
That's true. And I know also that you are a great gamer. What is your favorite game?
Oh, it changes from day to day. I've been playing Dungeons and Dragons since I was a kid, and you can tell by the gray hair on my head that that was a long time ago. Um, but lately, I've been getting into a game called Cipher System by a man that used to work for work for Wizards of the Coast. And so I play that quite a bit. But probably the one that's always been there, the game that I've always played and will always play, is Dungeons and Dragons.
Okay, I see. That's why you have such a topic today.
Exactly, and I got my 20-second ready to go.
Okay, great. This is amazing. So you can start right now your talk.
Okay, okay. So welcome everybody. Can you see my screen? Yes, there's my screen. So this talk is Dungeons, Dragons, and Graph Databases. It combines some of my favorite things: Dungeons and Dragons, of course, and graph databases, which I just think are really cool and interesting. And yeah, I thought, well, you could take this graph database and you could do a dungeon with them. Combine a couple of things I really like. So uh, hang on a second here. Got to get to the screen where I can actually advance my slides, right? Hang on. There we go. So I've already been introduced, but again, my name is Guy Royse, and I'm a developer advocate at Redis Labs. Um, Main things on this slide are just the social media links. The thing you're really going to care about, the thing I care about is that you follow me on Twitter at Guy Royce. But the thing that you're going to care about is not following me. You're going to care about the GitHub link there. I've got some sample code in here showing how to use a graph database to model a dungeon. It's all out there at github.com/Guy Royce, and I'll have a bigger link at the end. And that link at the bottom is if you want to read my out of date blog. Um, but this is a talk about Dungeons and Dragons as well as graph databases. And so I thought, as a fan of D&D for many, many years, I thought I should include my character sheet. So here's my character sheet. I gave myself an alignment of neutral good. I'm a dwarven bard. And the bard is because that's probably the closest thing to a performer, which is kind of what a developer advocate does, or at least a part of our job. And and the dwarf is because of the beard. So I've got my ability scores over there. I have, sort of mundane scores, and I gave myself a nice high charisma because that's what someone as narcissistic as me would do. If give yourself a high charisma. It also means with an intelligence of 8 and a wisdom of 8, this talk's going to be all sizzle and no steak. So, so yeah, that's my character sheet. I mean, I've been a gamer for decades, and as a gamer, you've got something you're trying to solve. You've got a problem. And that problem is that you want to level up your character. You want to get the gold. You want to get the experience so that you can improve your equipment and so you can face tougher challenges. And the question is how do you get these things? And the answer is you go to the dungeon, right? You go to the dungeon, and the dungeon is full of rooms, and those rooms can contain monsters and they can contain treasure. And so the dilemma is what rooms do I go to first, and in what order do I go to the rooms? If do I want to maximize my XP, then I need to go to the rooms with the tough monsters. But I don't want to go to a room with monsters too tough because then it might defeat me. I need a challenge, but not an overwhelming challenge. Likewise for treasure, if I'm just trying to level up my gear, can I find rooms full of treasure with no monsters? How do I get to them? What path should I go through the dungeon? And I thought, well, how do I navigate this dungeon? And I'm like, oh, I'm a programmer. I don't need to I can use my magical programming skills to solve any problem, right? How many times have you told yourself that? It's like, this sounds like a problem for technology. And so I can build a database that contains the rooms and the monsters and the treasure. And then I could query that database and figure out, how do I go through the dungeon to optimize my dungeon crawling experience? And I thought, well, let's look at a couple ways to do this. One way is we could use a relational database. This is sort of the tried and true historical way to do it. Relational database, you've got some tables with the joins and the schema and the SQL queries, and you just model that dungeon inside of a relational database. But there's another way we could do this, and we could model that dungeon using a graph database. And so I thought it'd be fun to compare and contrast these two ways of modeling a dungeon, and then the queries we can use against that dungeon to get, answer these important questions to maximize our gold and maximize our XP. So, everyone on board with the plan? We're going to compare relational databases and graph databases so that we can learn what graph databases are. And so the first question we need to ask is, what's a graph database? That's usually a good question for an intro topic like this. And this is actually, it is the right question, but there's a question underneath that. And that is, what's a graph? And so a graph is it's a set of nodes or vertices connected by relationships or edges. It's a mathematical thing. On this picture of a die 20 here, the vertex is the point. It's the nodes. It's the points on that platonic solid of a 20-sided die. And the edges, they're the edges connecting them. So the edges connect the vertices. And, this is, a 20-sided die. I've got another one right here in my hand. And these 20-sided dice and these solids like this certainly can be represented by graphs, but graphs are a more general concept. They don't have to be three-dimensional. They don't have to be dimensional at all. They are just a series of vertices connected via edges, or a series of nodes connected via relationships. And so we can look at graphs more of a draw it on the whiteboard sort of way. The simplest graph is the null graph. This is the graph that has no nodes and no edges, no relationships at all. There's nothing in here, nothing to see here. Move along. This is kind of a boring graph, but it is a valid graph. In the beginning, the graph was formless and void, right? So let's add some nodes to this graph. So here we've added nodes A through F. Nodes A through F are just kind of hanging out there in space. They're not related, but this is a perfectly valid graph. It's not very interesting because it's just entities. They're just vertices hanging out there, but there's no connections, no relationships. And relationships are what makes them a little more interesting. So let's add some relationships to our graph. And now we start getting into something that's a little more useful here. We've got some connections, like node A and node D are connected to each other, and nodes G and C are connected to each other. But it's not completely connected. Some of the nodes are isolated. In fact, some parts of the graph are isolated. So B and F, while related to each other, are still isolated from the larger graph. And even the larger graph in the middle, the big sort of the largest island in these chunks of islands is still isolated. And so you've got these pieces of the graph that when they're not fully connected, when they're not connected to each other, if there's no path from a node to another node, then those are isolated. So let's go ahead and connect all the nodes together because we don't want an isolated graph. If our dungeon were isolated, we would have rooms that we couldn't get to. And so here we've connected them all together. And now this graph is no longer got portions that are isolated, it's connected. And a connected graph means that every node on the graph has a path via other nodes and relationships to every other node. So no matter what node you pick on here, there's a path that can take you to any other node. You can actually have a fully connected graph. I don't have a picture of one, but this is the graph where every node is connected to every single node via direct relationship. And so you can think of a network as a fully connected graph. You've seen pictures of these where you draw a bunch of circles in a circle, and then they got lines connecting every single one. It looks like a star, a 5-pointed star. You could take it's a fully connected graph. Actually, no, it's not. But anyhow, you get the idea. So these are connected. One thing that we haven't done yet is we haven't added any arrows. This connected graph is also undirected. So A is related to B, but there's no information as to what direction that relationship goes. To make a directed graph, we just represent that using arrows instead. So now instead of A being connected to B and B being connected to A is connected to B in a direction. And so A maybe is, it's sort of hard to use a word other than direction to explain direction. But it's got you can think of it as A is connected to B, but B is not connected to A. A is sort of the lord and B is the vassal, right? There's a directionality to that relationship. And when we're talking about graphs, we can look at the degrees of nodes in a graph. And so the degree is the number of relationships that a node has. So node A in this example has a degree of 3 because it has 3 relationships, 2 outgoing and 1 incoming. And you can also refer to nodes in terms of their out degree and their in degree. Out degree is the number of relationships that are outgoing, and in degree is the number of relationships it has that are incoming. So node E has an in degree of 1, a degree of 1, and an out degree of 0. And so this is sort of how graphs work. There's one other important thing here, which is that there really aren't any rules. You can kind of connect anything to anything. Nodes can connect to each other multiple times. They can connect to each other in both directions. So here we have A and C are connecting to each other both ways. They can connect back to themselves. This particular graph we can draw in 2 dimensions on a piece of paper, but they don't have to even be able to do that. They can cross over in ways that you can't represent. They don't care about dimension. It's sort of not really what they're about. And so there's not really rules about what connects to what. A graph database is taking this graph structure and putting data on top of it. And so here we've got our nodes of our graph, and you can see that they're actually not nodes now. They're representing rooms and monsters and treasure of this dungeon that we want to model. And so we can take those nodes and we can give them a label. You can see here on the top left we have a monster, and then in red right below we have a monster. Alice and Bob. It's always Alice and Bob. Fun fact, Alice and Bob were my grandparents' names. So that always makes me kind of warm to think that I get to use their names in examples and software all the time. But here we've got Alice the elf. And so they've got a label here as monster, this node does, but it also has attributes, an ID and a challenge rating and an XP. Apparently, my grandmother was a bit of a badass. Challenge rating 7. Who knew, right? I just remember her as this nice old lady. But so we can lay that data on top of these nodes. And we can actually lay data on top of the relationships as well. And so here we've got a contains a relationship to say that the room contains a monster. Or we have a leads to relationship that says this room leads to another room. And now we've got something that looks like a dungeon. In fact, it looks very much like a dungeon. It's a database worthy of Mordor, right? So this is what a graph database is. You take that graph structure and you lay data on top of it. Sort of a little summary and sort of a couple points about graph databases here is you got these nodes and these relationships, or these vertices and these edges, or these connections. I tend to use all these terms interchangeably. Nodes represent items or nouns in the graph. They can have labels, so room, monster, treasure, and they can have attributes like ID or name. And they can stand alone. They can, just like a graph, you can have a graph that's completely disconnected. Every node is isolated. You can do that with a graph database as well. So these could just be nodes hanging out in space. Relationships connect those nodes together. They connect 2 and only 2 nodes. They have a type. In this example, leads to or contains. And they have a direction because this graph database is directional, has directionality. And nodes, relationships can have attributes as well, just like nodes can. And so here I've got an example of leads to with a distance of 45. Since this is D&D, that would be in feet, not meters. But they can have those attributes. However, I found that whenever I put attributes on relationships, it usually means that I'm slowly turning it into a node. And so I tend to avoid that. So I don't use that a ton. An important point with relationships between nodes too is that they don't exist without the node, which makes sense, right? If you take this graph that I have in my hand here, and I get rid of this vertex or this node right here, the edges, by definition, connect to nodes, and so there's nothing for them to connect to anymore, and so they go away as well. So if you delete a node from a graph database, the relationships to it go away as well. But if you delete a relationship, the node will stick around. So the nodes are sort of the boss, and the relationships are connecting them together. And I think this sort of ends up reading like sentences, right? So you've got a node. The room contains a monster. The room is the subject of the sentence. The monster is the direct object, and contains is that transitive verb that connects them together. And so your graph relationships tend to read like sentences. You know, the room contains a monster. The room contains a treasure. The room leads to another room. Reads like sentence. So that's the theory and the idea of what a graph database is. But let's get into the real bits and pieces, right? Let's get into some code and see what this looks like. Because we've still got a problem. We still need to figure out how to properly query this dungeon so that I know which rooms to go to and in what order. I need to figure out the shortest path between rooms, what rooms have the most treasure, what's the path to the room with the most treasure, what's the path to the room with the most XP, those sorts of things. I want to query this database. And we're going to build a relational database, and we're going to build a graph database to try and solve this problem. So, how do we talk to these things? Well, let's look at the query languages. For a relational database, you've got SQL. I'm going to assume that you've used SQL or SQL, sometimes as we say it. SQL is a programming language I actually learned in college in the early 90s and still use. I think it's the only one that I still use, which is kind of funny if you think about it. You know, programming languages come and go, but query languages seem to stick around a lot longer. And so when we talk to a relational database, we use SQL. To talk to a graph database, a popular query language is called Cypher. And Cypher is a query language that was developed by the folks over at Neo4j. And it's different, but similar at the same time. It kind of looks like a combination of ASCII art and a query language. It's got some elements that remind me of SQL, but then it's got these matchers that are terribly different from SQL. They're not anything like anything you see in SQL. And you can see them here in this picture here, right there, where you've got the, there we go. This guy right here, you got the treasure contains a room, contains a monster. That's sort of the ASCII art piece of it, the matching. And here's the one we can look at a little more closely. Here we have the room contains a monster, and we've got this matcher. And you can see that we're using parentheses and square brackets. And so the parentheses match room nodes, matches nodes. And if you're drawing this out, you know, you draw a circle for the node, right? And so that parenthesis sort of suggests circle. And so we have a parenthesis. And that colon room means match a node that has a label of room. And then the R in front of that says assign this to a variable for later use. And so this matches a room node. This matches a monster node in the same way that the room does. It's just a different label on that node. And this matches a contains relationship between them. And if you look at that bit in the middle there, you see there's an arrow. It's the query is expressing the directionality by using like this dash square brackets with the type of that relationship, and then a little arrow to sort of finish it off. And so this is this ASCII art that shows node, arrow, node, just like we're seeing in our picture up above. So these matchers will go through a graph structure like we've seen earlier. and will match that pattern in all the permutations that it's matchable in the graph. So this would return every room that contains a monster. And so we're going to, armed with this information here, we're going to look at how do we create rooms, how do we read rooms, how do we update delete rooms, and how to delete rooms. So hit the 4 basic CRUD operations for graph databases using SQL and Cypher. So if you're creating a room for a relational database, you've got a table, it's got a schema, the rooms have an ID and a name. In the graph, we've got nodes, they have an ID and a name, and they have a label of room. And so to create a room, assuming we have the table in SQL already, we use an insert statement, right? We insert into rooms, the columns we care about, and then we provide the values, and the insert happens. To do this sort of operation in Cypher, which is you probably haven't seen before, we use the create command. And so create takes a matching pattern. Create a room, create a node of type with a label of room, and assign it to the variable r so that we can do stuff with it later. Once we've created that, then we can set attributes on that room. Now, it's worth noting here that there's no schema, right? So we set r.id equals 1, r.name equals statue room, because every dungeon starts with a statue room, right? We could also say r.isTrapped equals false and add, another attribute on there. But we've created a room, and then we've set a couple of properties on it. So this is how we create nodes with Cypher. Now that we've written something into our databases, now we can query it. So here's how we query a room. Select ID name from rooms where ID is 1. This is like SQL 101, right? Select star from tables where blah, blah, blah. So that would return the statue room. The comparable thing in Cypher is using a match. So we'll say match, and then again, we provide that matching pattern. And it's the same one for when we created it. We want to match any node that has the label of room and assign it to R. And then we can put a where clause on there, which looks very, very much like SQL, where r.id is equal to 1. So of all the items in the graph that match pattern r:room, return, filter out only the ones where the ID is 1, and then return it. So match, where, return. This match where is worth noting because it's going to be repeated here in the next couple queries. So we match a thing to query, find a pattern in the graph, where to narrow it down, and then return it. If we want to update a room, we use a SQL update statement. Update rooms, set name where ID equals ID we want to update. So the statue room is getting an upgrade. It's now a statue hall. To do this with Cypher, we do a match where, just like we did with the read. Find that room with the ID of 1. But instead of doing a return, we set a property on it. So we set the name of the room to statue hall. And again, if we wanted to add attributes that weren't there before, we could add those using the same syntax. And so we could also say set r.name equals statue hall, comma, r.trapped equals true. And now it would be a trapped statue hall. But again, it's that match where, and then we're just setting the attributes that we want. To delete a room, always the fun operation, delete, isn't it? So in SQL, we delete from rooms where ID equals 1. Make sure you get that where clause or someone's going to be really angry, or maybe you, right? It's too bad it's not like video games where, you do something stupid in a video game, you can rage quit. But when you do something stupid in production, quitting isn't really what happens in that scenario. But so we delete from rooms where ID equals 1, right? To do this in graph, again, it's that match where. Match a room where the ID is 1, and then delete it. Don't return it. Don't set a thing. Delete it. But, very similar query. So that's a super, super basic intro to Cypher queries for just manipulating nodes in your graph. I want to make a note on this that there is another syntax that you can use. The matching can also, so I've been using this match where syntax, but you can also sort of inline this and say match a node with the label of room, and then inside of curly braces you can put properties that you want to, or attributes you want to match on. And so this is equivalent to saying where the room ID is 1, And you can comma separate these inside of the curly braces. The syntax is actually the same as you would use in in JavaScript. So that's an alternate syntax for matching. And you can also use this when you're creating. So here we created a room, which immediately creates a node called with type room, and then set things. But we could also just inline those properties as well. We could say create a room and set the ID and the name to these things. And you'll notice actually in this query that I took the R off of in front of there. It's because I don't need a variable to refer to. I can just create the node with the label room, and my properties are part of that. So I don't need to reference that. So I don't need that R in front of the room anymore. And so we can create monsters. And here again, I did this inline syntax for creating monsters. It's the same as creating a room. And we can create treasures. And here I mixed it. So I said create treasure T, set the ID and the gold piece value in line with the curly braces, but then go ahead and use the set command to set the name. So you can mix and match these two. So that's all the CRUD operations for manipulating nodes. This gives us a relational database that looks like this. We've got rooms, we got monsters, we got treasures, and here's our rows. And a graph database that looks like this. And we've got all these nodes, they're just hanging out in space. They're not related to each other. Everything's isolated. I guess you could say this is a fully disconnected graph. So we need to do something a little more interesting than just inserting and deleting things. We need to put monsters in a room. And we need to put treasure in a room. So let's put a monster in a room. In a relational database, to put a monster in the room, well, based on what we have for our database so far, you can't. And so we need to alter the table monsters to add a room ID. We need to create a foreign key that allows us to get to associate monsters with a particular room. This will allow Alice to be in the statue room and Bob to be in whatever room 3 is, the armory. And so we alter that table, adding a room ID, and then we update the monsters to set values for those room IDs. And so this places Alice in room 1 and Bob in room 3. So it puts Grandma in the statue room and Grandpa in the armory. Sounds right. And so this is how you do this in a relational database. This is, again, creating a one-to-many relationship. This is tried and true relational database pattern. How do we do this comparable thing in a graph database? Well, we need to create a relationship. And to do that, we can do matching again. And here we're matching a room with an ID of 1, assigning it to R in the first line. And we can have a second match in our same query that matches another node and assigns it to M. So we're going to match the room, we're going to match the monster. And now those are R and M. And then we can create a pattern in the graph, create a room, create a R, create that relationship of contains between R and M. R and M already exist. They won't be created, but the contains relationship between them will be created. And so you match the two things you want and you create that relationship between them. There's a temptation to do this when you are doing create. You're like, well, do I need to do the matching? Can I just, instead of doing like a match where or something like that, can I do a create with just the node the way I want and match that way automatically? The answer is no, you can't. If you use this syntax, you will create duplicate versions of the things that you just had So now we have 2 rooms with an ID of 1 and 2 monsters with an ID of 4. And then you will create a relationship from those duplicated nodes, but the nodes you wanted to relate won't be related. So this was a mistake I made when I was first getting into this stuff. I'm just sharing it with you so that you don't make the same mistake. So this is how we put a monster in a room. Putting a treasure in the room is going to be exactly the same. We're going to alter the table. We're going to create the relationships for our relational database. And for our graph database, we're going to match the room and the treasure and then create a contains relationship again. So similar problem. Works exactly the same. So let's look at our relational database so far. Still pretty tidy. We've got rooms, and there's a one-to-many relationship with treasure and a one-to-many relationship with monsters. So room can have multiple monsters and multiple treasures. I want to find the rooms with multiple treasures and no monsters because I'm greedy like that. Let's look at our graph database so far. Here we've got some isolated portions of the graph, but there is some relationships now. It's getting a little more interesting, right? Rooms have monsters, rooms have treasures. We can see that if I want to maximize my my treasure, probably I should go to the barracks because there's a +1 sword worth 1,250 gold pieces and no monster. So I'm going to go there. Get the +1 sword, then I can use it against the monsters, right? But this graph isn't complete. It's not a complete representation of the dungeon, and neither is the relational database. But we can start doing some munchkinning. We can go in and start doing some queries to optimize what we're looking for. And so let's go and see if we can find the best monster rooms and the best treasure rooms. Maybe we can get a prioritized list of the monsters and the treasure that we want to go after. So first we can farm all the XP. Here's our relational database. Here's how we would do this with with SQL. We want to get a list of all the rooms in highest XP order down. We would do that with a classic join. So we select the columns we care about, the room and the XP, from the two rooms, rooms and monsters, from the two tables, rooms and monsters. And then we filter where the ID and of the room matches the room ID on the monster table. So we match those foreign keys together so that we don't get a Cartesian product out. And we order it descending by the experience points, putting the highest XP value stuff at the top of the list. This will give us a list of all the rooms we should hit in the order that we should hit them based on XP. So pretty simple query. How would we do that with a cipher? Well, it's actually fairly similar. We want to match all rooms that contain monsters. So we create this matching pattern of a room contains a monster. It will walk the entire graph and find every instance of a room that contains a monster, everything that matches that. And then we return the ID, the name, and the experience points and order it by the experience points. And this will give us a list very similar to the list from the relational database of rooms with their name and their XP value, sorted by largest to smallest. So this is a way we could farm all the XP. Getting all the gold is, of course, going to be a very similar process. We just join on treasures instead of monsters. And again, with the graph, it's the same thing. We just swap out treasure for monsters and swap out gold piece for experience points. And so here we can go through and match all those rooms that contain treasure. Again, it walks the graph, finds everything, returns it, sorts it. So that's kind of neat, right? But so what, right? So far, the graph database hasn't really done anything that the relational database can't do. It's schemaless, which can be nice. But I've been able to do all the queries in graph and in relational databases that I need to just get these prioritized lists. Excuse me. So we need a way to start do the interesting thing, which is connect the rooms. So let's connect some rooms. How do we get a room to connect to another room? How do we know that this room leads to another room? How do we do that with a relational database? How do we do that with a graph database? To connect rooms with a relational database, well, there's no easy way to do this, really. We have to create a many-to-many mapping table that maps our rooms to rooms. And so we have to create a new table. We don't have to alter any schemas this time, but we do have to create a new table that allows you to relate a room to a room. And it's got a from ID and a to ID. Then to relate, say, the statue room to the barracks, we have to insert into that table the two IDs. And now we've got a one-way relationship from the statue room to the barracks. This is a little unintuitive. I mean, it works, and I've done this in production myself many times, but it's hard to think about sometimes. How do we do this with a graph database? Well, it turns out that in graph, it's just another relationship. And so just like you would relate a room to a monster by having it with a contains, you can relate a room to a room with a leads. And so here we just match the two rooms that we care about, and then we create that relationship between them. It's exactly the same pattern as if we're putting a monster in a room or we're putting treasure in a room, because it's just nodes in space connected with relationships. There's no schema to modify. There's no foreign keys to really manage. You just say this room leads to that room. And so here we've got the armory leading to the barracks and vice versa. So that's how we do relationships, how we connect to rooms in both graph and relational. So we can see our relational database has kind of gotten big and a little bit hard to think about. It's not huge. I mean, it's still manageable. And our graph database is, well, it looks like our dungeon, doesn't it? This looks like where we came in. Cool. So given these databases, now we can be more than just a munchkin. We can be a super munchkin. And we can find pathing queries. So one of the things that graph does well that is hard in relational databases is finding paths. I want to find what path through the rooms leads me to the room with the biggest treasure. To do that with a relational database, you'd have to have joins back on itself n number of times. You end up with sort of like a recursive joins. And I'm not even sure if that's possible in SQL. I haven't done it. And so that's kind of a tough problem for SQL. But Graph does it naturally. It's actually set up to do pathing matches through the graph. And it does this in Cypher with the asterisk. So if we add an asterisk to this relationship, to this matcher, what we do is we say room 1, any room, room 2, any room, leads to star. So that star says, hop over multiple nodes in the graph as long as there leads to relationships. So if you have a room that leads to a room, that matches this pattern. You have a room that leads to a room that leads to a room, that matches this pattern. You have a room that leads to a room that leads to a room that leads to a room, and so on and so on. Anywhere from 1 to infinity hops to connect those rooms together, this pattern will match that. So it doesn't match just a 1-to-1. It'll hop over them, which all of a sudden is a lot more powerful. I just added one character, and all of a sudden I can query this stuff. You can also use a couple numbers there. You might want to limit it. You might say, I want to see all the rooms within 3 hops of myself. That's what this query would do. Minimum hop of 1, so at least 1 hop, and at most 3 hops. And you can put any numbers you want in here. You know, give me a list of all the rooms that are 4 or 5 hops away from me. You could put those values in. And so this would match those patterns. And again, these patterns walk that entire graph and find them. One question you might have if we look at this previous one, whoops, there it is what keeps this thing from doing infinite loops? Because there's infinite number of paths through this graph, right? If you've got a bunch of nodes in a circle, you can just keep going around that circle as many times as you want. It won't do that. The graph database solves that problem. It won't run forever. So no worry about that. Okay. So let's do some interesting queries. Let's look for nearby rooms. So this is going to give me a list of all the rooms that are within 3 hops of me, within 3 relationships of me. So it matches, presumably I'm in room 1, the statue room, and I want to find all the rooms that are up to 3 away. This query will return them by matching using the lead star 1.3. It'll return a list of all the IDs and the names of the rooms that are around me, which is kind of interesting. It lets me know where I'm at and what's around me. But let's find rooms that are near me with the most gold so I know which room to go to next. Well, all you have to do is extend that query. You got a room that you're in, leads to 1 to 3 hops away, another room that must contain a treasure. And so that will match all rooms that contain treasures that are within 3 hops of you. And then we return that ID, the name, and the gold piece value. And then here I've ordered it ascending by gold piece and put a limit 1. So it gives me the room with the most treasure that's within 3 hops of me. So where am I going next? This will tell me where to go next. So this is a similar query to the previous one, just a couple extra things tacked on there. We could find the longest path through the dungeon. Let's say I'm a completionist and I want to make sure I hit every room in the dungeon. Well, here we could do that with that room leading to room with a star. So match all rooms that can lead to all rooms. But we can capture the path that match will match, all the paths. And then we can execute functions against it in our cipher query. So we assign that path to a variable p right here. And then we can say, well, give me a list of the nodes that are in that path. Give me the length of that path and name it length. And then I can order by that length descending. So the biggest one floats to the top. And then I can limit one to get just the top item. This will give me the longest path through the entire dungeon that hits every single room. The room with the biggest treasure. That sounds useful. So there's another clause in Cypher you can use with on your match that allows you to store variables for future use, in a sense. So here we're matching all treasures, all nodes that are treasure nodes, with, and then we're using an aggregation function, max. So you get all the gold pieces of all the rooms, of all the treasures, and then this return the maximum of all those, as opposed to like sum or average or something like that. And then we're going to give that a name as max GP. So we've got a maximum gold piece value. Then with that, we can match all the rooms that contain treasures where the gold piece value is equal to that max gold piece value, and return those. So that this with allows us to sort of store variables for later use. And here we've sort of combined all of these ideas together. We want to get a path from the room I'm in to the room with the most gold. So we've got that match with max gold piece as max GP. So we're getting our maximum gold piece value in the dungeon. And then we're matching the room that contains that that treasure. And we're setting that room ID as the destination. Then, using another with there. Then we match from the starting room, which we hard code as a 1, to the stop room, which is the destination ID, a path from where, so we map a path to that room from where we're currently at. And we capture that P, and then we can take that path, ask what nodes are in the path so we know how to get there, and get a length so we know how far it is. And then we order it and limit it. So we get the best path. And we got the shortest path to the room with the most treasure. So this fairly complex cipher query can tell us that. So these are some neat queries. I've got a demo. I don't know if I have time to do that. I think I'm almost done here. But I also started a couple minutes late, so I don't know if there's any rollover there. But I've got a quick demo just to show you that this is real. I'll run one query really quick. I built a random dungeon generator. And I kind of want to show it off, honestly. So this is all out on GitHub, so you can go check it out. It's written in Node. And the main thing here is that I can do npm start, and it will hit a cloud-based instance of Redis Graph that I'm using, and generate a dungeon. And so if I go to that cloud-based instance here, I'm using Redis Insight here. I can say match and return n. So this is like select star from a graph database. And this will return me all the nodes in the graph. If I go to a tabular view, I'll see the names of the nodes. I've got randomly, this is the random dungeon name, the Fabled Sewers of Jarzemez. We got different rooms within the dungeon here. We go to the node view here. We can look, there's our dungeon node. Let me zoom in here. You click the plus. Right, and we can see that it has an entrance to the filthy jail, which contains the dwarven lance and the armor of Scandwissa Preston, whoever that is. And I can generate this again really quick. And we'll see, and if I go out and query this again, we'll see that the dungeon has changed. The dungeon is now the shattered sewers of Slurlub. Slurlub. Of course, Slurlub. I know Slurlub. And so I'm just going to do one of the cool queries here to show that this isn't vaporware. And I've cheated here, and I've got them all ready to go. So here's the shortest path to the most gold. It's the one I just showed you all. I go out here and run that query. You can see why I don't want to type it in, right? So it works better this way. And so we get 4 nodes. Node 0, which is a room. And so this is the path. So here's our rooms. Here's the last item in there. The Shattered Defile is the room that has the most treasure. And I'm currently in the Grand Room. So that is the path that will get us the most gold. If I look at this from a graph view, I should be able to see there's a chest of coins worth 75. That is certainly not the greatest treasure in the room, but if I walked around the graph a bit, I could find it pretty easily. I just need to remember which one was the end node. It fell out of my head by the time I switched screens. But anyhow, yeah. So I think I'm about out of time. Let me head back to my slides here. So I've given you sort of a fun and ridiculous example of what you can use graph databases for. It actually is a really intuitive example because they're nouns and you're connecting them with verbs, right? But there's a lot of practical applications as well. Social networks is sort of the canonical example of a practical application for a graph database. I'm friends with this other person. I follow this person. I like their post. These are very natural graph relationships. Genealogy, keeping track of your ancestors. Alice and Bob beget Sally, who beget Guy, who beget Luke. Sort of that family network. Genealogy is like a social network, but over the decades. But it's a very natural relationship, graph relationship as well. Transportation networks are a natural graph. You can think of bus stations and train stations and subway stations as nodes, and the connected via that transportation. And I like the logistics example, where you say you've got a store that has some poison, some lettuce that's got some E. coli on it. You could track back that lettuce to the particular farm using a graph database. Or epidemiology is another good and I suppose rather timely example of using a graph database, where you can say, well, this person had contact with this person, had contact with this person. So contact tracing is another natural graph problem. If you're looking to play with this yourselves, go check out Redis Graph. It's free. Source code's all available if you're so inclined. I usually do that via Docker. If you want to learn more about the Cypher query language is created by Neo4j. And so you can, there's a link there to the detailed specification. And Neo4j, of course, has open sourced this to the community. Everyone can use the Cypher query, which is why we're able to use it at opencypher.org. And I've got a blog post I wrote about Redis Graph as well, which is some of the stuff I talked about in the talk, but it's some more concrete examples that are easier to copy and paste. I work at Redis Labs, as I mentioned, so go check us out. We've got a Discord server. I like that the link for the Discord server looks like your game master has sneezed. It's like GM Kachu. But I'm always on there, and if you have any graph questions or any Redis questions, you can always ask. We got community forums online if you want to do it like slow Discord. And Redis University has courses that you can sign up for free. We run them periodically, so go get some free training. Codes, slides, and 3.6 plus 2 pull requests are available out at GitHub at this URL. This QR code will take you to that URL. I promise it will not rickroll you. That QR code, it will never give you up, and it will never let you down. It will totally go to, it won't run around and take you to other sites that you don't want to go to. So that's pretty much all I got. Again, my name's Guy Royse. Give me a follow, check out the code, and thanks a lot.
Guys, thank you very much for such an impressive talk. It was amazing.
Thank you very much.
We have 10 minutes for Q&A session, so please join by the link that our org team sent to you. And meanwhile, guys that were looking and were following your presentation also will join Q&A chat. I once again appreciate that you joined our event. It was a great pleasure to have you and also a great honor. And we hope that next year we will see you offline here in Kiev, in
That
Ukraine.
would be amazing. I haven't been to Kiev yet. I'd love to come.
Yeah, you should. You should come.
Yeah. Excellent. Well, thank you very much for having me. It's much appreciated. And I'm assuming the link to the Q&A is in my email.
Yes, right. Yes,
Okay.
right in your email.
Okay. I will
Thank you.
click post haste.